we're going to look at the, so someone has answered my question. Okay, good, it is. Okay, so we're considering the gross-P-H2 equation, which I wrote down a couple of months ago. Here it is. And so it's for a complex valued wave function, psi. So for the rest of for the next couple of weeks, I'll be discussing it on a bounded open subset of R2. I've had this problem recently where I say to people, I'm admiring, I say, oh, look at that beautiful subset if the sun is going down and they're beautiful clouds, and now I'm making the opposite mistake. Okay, so we have a bounded open subset of R2 with smooth boundary. In fact, it'll be simply connected also. And there's the equation, we've seen it before. So to remind you of this notation I use, and so for complex numbers, V and W, I put these parentheses around it to denote a real inner product. So here I think of V and W as being vectors in R2, and I think they're inner product. That's what this is. Okay, and so if I'm thinking this way, then multiplication by I is rotation by 90 degrees in the counterclockwise direction. And so, for example, the inner product, the real inner product of IV with W, I mean, so that you can see the inner product is symmetric rather than rather than conjugate symmetric. If I, so this is the same as, well, let's say, I don't need to belabor this, but so if I multiply both this first and the second thing by I, I've rotated both of them by 90 degrees, doesn't change the inner product, and I get the inner product of W with of IW with minus V. Okay, so that's clear. And then if you write it out, we can see that this is exactly the determinant of this 2x2 matrix, whose columns are V and W. Okay, so that's notation we'll use. Okay, and then there are these physical quantities, the energy density, the mass density, the current or momentum density, and then the vorticity. So let me make a remark here. Right, so this is, so this is how we think of this in practice. This little j is rho squared, the density times the gradient in the phase. And in fact, one also thinks, and so we think of, so the gradient of the phase is the velocity. Right, and so if I have a fluid with a certain density being transported along by a certain velocity vector field, then the density times the velocity is the momentum density. Okay, so it's the imperceptible form of it's mdv, if you like, where and mv is momentum. Okay, and then finally the vorticity is defined in this way. And let's do this little calculation. So that's 1/2 this minus the d2 of the first component of J, which is I psi d1 psi plus d1 of the second component. And so what happens when I do this? Using the product rule, I get a term involving minus I d2 psi d1 psi plus I d1 psi d2 psi. And then the other terms, I'll have an I psi, the inner product with the d1, d2 psi twice with opposite signs. So those cancel. And if I look up here, I can see that, I mean, so the second term here is, we saw this is the determinant of the matrix whose columns are d1 psi, thought of as a vector in R2, and d2 psi. And the other thing is the same. What do? I switch the columns of the vector, and I put a minus sign in front. I take the determinant. So these two things are equal, and they're both equal to this. And that's really a Jacobian determinant, right? It's the determinant of, I write the 2 by 2. So here I'm thinking of psi as being an R2 valued function. It's determined as a 2 by 2 matrix. It's greater than 2 by 2 matrix as the determinant. So it's this Jacobian determinant. Okay, good. So this is both a mathematically and a physically natural quantity as the curl of the momentum. Okay, and so that was, oops. So I wanted. Okay, and so then we proved earlier some we stated and proved some conservation laws. I think I stated the first two, which are easy, and I proved the third one, and then the fourth one follows immediately from the third one. Okay, and so these are the basic conservation laws for energy, mass, momentum, and vorticity. Okay, and we're again using this notation where grad psi, tensor grad psi, is the entry whose k L component is this real inner product of the k and L derivatives of psi. Okay, and so for example, I'll write capital E of psi to denote the integral little e, the total energy. And I will always consider situations where the energy is, it may be diverging. In fact, it will be diverging, but it'll be diverging at most logarithmically. And so then, so since if this quantity is bounded by log epsilon, then I can say that the L2 norm of psi squared minus 1 is bounded by a constant times, okay, there's a constant here. A constant times epsilon times log epsilon to 1. So in an L2 sense, the modulus is very close to 1. In this regime, I will always consider. Okay, and so so our goal is to, I guess I said, study vortex dynamics, and we'll rely crucially on these equations. And so, okay, so let's move on. So here's the so we're proving an analog of theorems that we prove earlier, and there we really use the Biot-Savart formula. We use the vorticity transport formula, okay, we used the pseudo energy. The reason I'm considering a bounded domain in R2 is because I want the energy to be finite. So I don't want to consider all of R2 as I did before. Okay, and so essentially all the tools we had before are missing. What will we use instead? And so the kind of thing we'll use, I stated a sample theorem here, and let's look at it. So what do I mean? So I should define things. Well, let's let me draw a picture. But okay, so first of all, I've written an F, so the flat norm here. We saw a flat norm before. I'll have a different variant here. So the flat norm will be the supremum of this, where let's say phi is in W1. If phi is a Lipschitz function, with 0 boundary conditions. And let's say the L infinity norm of the gradient is bounded by 1. So it's a 1 Lipschitz function with 0 boundary conditions. Okay, and so I'll prove some things about this a bit later today. This is a bit like the flat norm we were discussing in the 3D Euler equations. It has those nice similar geometric properties. Okay, and so the this theorem says, assume that so in particular, if this omega of psi is so then here's a picture of the theorem. Here's the domain D. I have a few points, A1, A2, A3, and I assume that they're bounded away from each other. So the distance, the closest distance of any 2 points, A1, A2 to each other, is bounded away from there, and they're bounded away from the boundary. So it might be better to say they're bigger than some rho naught, which is a positive number. Okay, so okay, so that's the assumption, and that's assumption 1. And then I assume that the vorticity is close to. Okay, then I also assume that I have multiplicities di, who are integers with absolute value plus or minus 1. Okay, so one feature we will see for the Gross-Spitievsky equation as opposed to the Euler equation is that the vorticity is very naturally quantized. So it comes in, and there should be a factor of pi here. So the vorticity very naturally wants to look like a bunch of delta functions with multiplicities being an integer multiple of pi. Okay, and so I assume that in this weak norm, the vorticity is concentrated around these. It looks like these delta functions, and there's a mistake here. Okay, and so we should think of this as saying that, well, the vorticity is concentrated around here and around here and around there on a, well, no, actually, sorry, here's what it says. That what this is seriously saying, we'll see this more in the future, is that they're balls of radius, say rho sub a over 10, and that within each ball, so we should think this thing saying that, you know, on a kind of a coarse scale, the vorticity looks like these sum of delta functions, where the coarse scale is a little bit smaller than this minimum intervortex distance. Okay, so that's assumption 1. And assumption 2 is that the energy is not too big. Not too big means this, m pi log 1 over epsilon plus a constant. And the conclusion is that if this is true, then in fact, we can find points, if I shift the points a little bit. So, okay, well, let's look at the conclusion. So the conclusion is that there exist points, I don't know, C1 and C2 and C3, such that the vorticity is really very, very sharply concentrated around these points. Okay, so if I change the A's here, and again, this factor of pi is missing. If I change the A's here to the C's here, then instead of looking like, instead of the vorticity looking like a bunch of points on this sort of coarse rho sub A scale, the vorticity represents a bunch of points on some tiny epsilon of the alpha scale. So okay, and so what this says is that you know, the vorticity wants to be concentrated. This is good because remember when we studied the Euler equation, we devoted a lot of effort to, so we studied vortex dynamics, and we first, first we said we considered a single point vortex in background flow, and we could control the motion of a center of vorticity very well and the growth of the second moment. But it could still, we had to worry about it sending out these little tendrils everywhere in every direction. Here, the energy controls the vorticity concentration quite well. And so if I just have, if I know that they're, so let's say once we know the conclusion of this lemma, we can say that in fact, under these situations, under these hypotheses, in fact, within each ball of radius rho d alpha over 10, there's a really quantized vortex, something who looks a lot like a delta function with mass pi, plus or minus pi. And so within each ball of radius rho alpha over 10, there's some such point. And so if we assume that if we know roughly the vortex locations and we have some control of the energy, then in fact, there are these very sharply concentrated vortices. Okay, and so that's good. That's a kind of thing that one definitely does not have for the Euler equations. And another thing, I didn't state this, and so my goal here will be to, we won't have time to prove this theorem in detail, but we can sketch the ideas behind it and hopefully make it plausible and give you some kind of intuitive feeling for why it's true. So that's the goal of this. Another theorem is, and so here's what we'll do when we study the gross PDS equation. The energy is conserved, right? I don't know if I didn't emphasize this, but or I forgot to write it. But I'll always consider Neumann boundary conditions. Let's write this here. I'll always consider Neumann boundary conditions. And so if I have that, then I can integrate by parts, and I will have this. And so the energy will be conserved with Neumann boundary data. And so for example, I can solve the equations with initial vorticity concentrated sharply around a bunch of points, and with the energy on satisfying this hypothesis here. And then I wait a little while, and it'll turn out that the vorticity evolves continuously in time for a little while at least. The vorticity remains kind of concentrated around its initial points, and so the energy hypothesis will continue to hold for all time, and this will continue to hold for short times, and that will tell me that for short times at least, the vorticity remains very, very concentrated around some points, which is already useful information. Okay, so another theorem, this one I didn't state in full. Oops, I didn't. Okay, so here's another theorem. So in practice, when we're studying the gross PDS equation, we'll be able to assume that this is true, that there are some points around which the vorticity is concentrated on some scale that was much smaller than 1. The length scale is much smaller than 1. And so here I'm assuming that, so I'm imagining that C sub 1 up to C sub m are the points I found with the previous theorem. I started by having some kind of coarse information about where the vortices are. The previous theorem says, well, I can find some nearby points where the vortices are really, really concentrated. I assume that their intervortex distance is bounded away from 0, and their distance to the boundary is bounded away from 0 by this number rho naught. And then I'm entitled, based on the previous theorem, to assume that once I put the factor of pi here, this is true, then what happens is that we have a very precise, so these will be, say, we have very precise energy asymptotics, where what is W? And so W is going to be the did I add this extra stuff? No, I didn't. Okay, and so first I have I not equal to J of the log of, sorry, of di dj log of xi minus xj, and then I would have the sum over all I and j of some h of xi xj, where where, how's this go? So h is the regular part of the Green's function. i.e. For all y in omega, if I view it as a function of x, in, it's not, it's d, and h of x, y is something like minus log of x minus y for x in the boundary of the domain. Okay, so that's, I may have some signs wrong, I may have some constants wrong. Here's the point, so here's a remark. We saw this a long time ago. So remember when we, after proving the point vortex dynamics theorem for R2, we discussed what it would, for the Euler equations in R2, we discussed what it would look like if we were considering the Euler equations on a bounded domain. And so the point vortex ODEs on the bounded domain D are exactly, let's say, d xi dt is the gradient orthogonal with respect to xi of w of okay, so if you remember the so what's this say? It says that there's a well, okay, another way of writing this is and I forgot the di dj. Okay. Okay. And so here we have I and j go from 1 to n, and I is not equal to j. And then we have the diagonal terms. Okay, di squared is 1. And here, and this g is the okay. And so so what happens? It's easier to understand the equation this way. And so what happens is that each vortex generates a flow whose and this is, I'm sorry, I'm getting this all wrong. Okay, so each vortex generates a flow within the domain, and so it's rotational and it's tangent on the boundary, and that's exactly grad perp of this Green's function g. And so then each vortex is convected by the sum of the flows generated by its neighbors, but also there's a contribution reflecting its own interaction with the boundary, and that's this last term h of xi xi. And there's a grad perp here too. So sorry for all the typos. Okay. Anyway, the point is that the thing appearing in this asymptotic expansion for the energy is exactly the if you like, the Hamiltonian who generates the velocity field for the point vortex ODEs. Okay, and so no, I'm sorry. This wasn't supposed to be here. So the so here's where the orthogonal gradient appears. I had it right first time. Okay, and so the okay, so that's that. Anyway, the so my goal, as I said, is to so what we'll do is we'll rely on these theorems. And so what do they involve? They involve a kind of an intimate relation between energy and vorticity. If we know where the vortices are, that gives a lot of information with the energy. And if we control the energy, that tells us something with the vorticity concentration. It tells us it's possible to look at vortices with high precision. So I want to understand why these are true, and without giving full proofs, and then how we use these to analyze the dynamics of vortices for gross PSE. Okay, and so so the plan is to understand energy and vorticity. And so elements of the above theorems. And then see how, so use these to study point vortex dynamics. Okay, and so so let's see. So first, let's do an example first. So the most basic example. Say psi is a function from the unit ball, and let's say psi of r e I theta in polar coordinates is f of r e I theta. And let's consider energy and vorticity. So let's compute the energy and vorticity for this thing. So energy Okay, and so in terms of this, so this is just a, the phase rotates once, it's e to the I theta times some amplitude f. Okay, and so we easily compute that the okay, so if I differentiate this, then when I differentiate with respect to r, I'll get f prime squared. When I differentiate with respect to theta, I'll get f squared over 2r squared. And then I'll have a term f squared minus 1 squared over 4 epsilon squared. Okay, so then the integral will be 2 pi when I integrate out the angular variable times the integral from 0 to say 1 of f prime squared over 2 plus f squared over 2r squared plus f squared minus 1 squared over 4 epsilon squared at r dr, and I already integrated with respect to theta. Okay, and so let's, did I do this already? I can't remember, but I might have done this a few weeks ago. This may be a review. Okay, so let's look at this. How small can this be? Well, if I just over 2r plus r. Okay, so here's what I have. And so I can see that if, well, actually I liked it better like this. Okay, I can see that if r is less than epsilon, then the dangerous term is the first one, and then so the integrand so if r is less than epsilon, so to minimize, I want f to be about 0 if r is less than epsilon, and f should be about 1 if r is greater than epsilon, because so when r is less than epsilon, I want to neutralize the first term, the 1 over r squared term, and otherwise the second term. And so, so let's assume, so let's just consider, let's take f of this form. And so already if r is, I mean, one thing I could do is I could pointwise minimize this integrand. That would be a little bit smarter. But anyway, the integrand, just being casual for now. So the, say, epsilon out to 1 of okay, and so I can see that the setting f equal to 1, for example, for r greater than epsilon, I'll just get this, which is like, and there's a pi log 1 over epsilon. And then plus O of 1. So I can see that the contribution from 0 to epsilon should be order 1. I would have something of order 1 over epsilon squared integrated. That'll give an integral order 1 from the other term. Okay, And so this crude computation explains why we see these factors of pi log 1 over epsilon everywhere in this theory. So what about vorticity? Well, also, I mean, to back up, so what we can see is that if I want the I mean, for example, if yeah, well, I mean, we know that the L2 norm so we can see that we can have energy of order pi log 1 epsilon if you're a bit more careful. If the energy is that big, then we know that that the set where the modulus is, say, less than a half can't be much bigger than order. It can have volume much larger than epsilon squared times some small factor. And so really it's got the F has got to look like as described to have small energy. It's on a scale of epsilon. And sort of vorticity, well, we have so for example, if I compute the integral of f over any ball centered at the origin, the vorticity omega of psi, this is by Stokes' theorem, this is going to be J of psi, the tangent over the boundary of the ball. And this is F squared of S times the gradient of theta dot the tangent over the boundary of the ball. So this F squared I can bring outside because it's a constant here, it depends only on S. And so this is then 2 pi. I'm sorry, there's a factor of a half here, isn't there? So I get a pi times F squared of S, which will be basically pi if the energy is small, because if the energy is small, then if S is much bigger than epsilon, since then the small energy implies that F of S is like 1, small being not wildly divergent. Okay, so so another way to see this is that I have this function defined on the unit ball, and it what's it look like? Well, so this function f, once I go a distance more than epsilon away from the origin, it's basically taking values in the unit circle. It's basically mapping into S1. And it maps, say, a epsilon neighborhood of the origin, or a little bit bigger. The image of that will cover all of the unit ball. So, okay, let's not write it down. But so the point is that this vorticity is a Jacobian. It's a change of variables factor, so it tells us how areas change. And so in particular, the integral over the small ball around the origin is going to be the area of the image of that small ball, which is basically the whole unit disk. And so that's why a small ball around the origin, the integral that will be pi. And then the integral of this vorticity around this region outside here, well, that whole region basically gets mapped in the unit circle, gets mapped in a set with a very small area. And so that too will have very small. Okay, so that's a crude calculation. So let me describe how I will prove theorems like this. And so this is also to review what the flat norm means, or to see what it means in this context. And so this is a theorem that says under some hypotheses, the vorticity is very sharply concentrated. Let's call this theorem 1. So theorem 1 says, some hypotheses imply so how to prove, and I mean, how to prove it, and so the point is, what does the estimate mean? What does it mean? So we'll show, we'll argue at least, the hypotheses imply that there exist balls E1 up to BK in D, such that the sum of the radii what did I say? I think the conclusion was that was a conclusion, yes. Here. Okay, so we'll show that that's true. And to the set of points X where psi of X is less than 1/2 is contained in the union of these balls. And so I claim that, and then we'll define. Then the conclusion holds. If Xi is the center of the ith ball, and Di, looking up here at these things, Di is the degree or the winding number of psi on the ith ball. Okay, so so we'll argue that the hypotheses imply that there are a bunch of small balls, and outside those small balls, the modulus is bigger than 1/2. Then it will, and then we will argue that this implies this vorticity concentration statement. Let me see. I'd like to sketch the proof proof that. Okay, and so the point is, I'll write down these estimates often, things like this, and this is what they mean. They mean that I can find these balls whose radii after some power of epsilon, a tiny number, and then so one point is we think of the vorticity as being essentially this concentrated in the set where. Well, yeah, so in some sense, one can think of being concentrated in the set where the modulus of psi is less than 1/2. And remember, the modulus of psi wants to be 1 most of the time because in this regime, psi squared minus 1 is very close to, is very small in L2. Okay. And so, okay, and so this means we, the vortices is concentrated in these balls in the sense described below. So let's, I don't know if I have time for this, but I'll start. Well, okay, let's put it this way. So if I could replace, so the conclusion is clear. Note, the conclusion is clear. If psi has modulus 1 outside the union of the balls, since then what happens? So what do I have to do? I have to multiply psi against, I have to multiply the vorticity against a test function and integrate over the remaining. Okay, and I should have said the balls are disjoint. Pairwise disjoint. And so the first point is since outside the balls, psi squared is 1. Let me assume, so I'll always assume that psi is smooth, and I can, so I'm considering guys in H1, but I can always regularize, I can modify them, do my computation for smooth functions, and then get the conclusions. So I'll do calculus without worrying very much. This is true, so I can differentiate to find that grad psi dot psi is 0, which implies that the gradient psi here is a 2x2 matrix. It has a 0 eigenvalue. Contains okay. So so in open sets where the modulus is 1, the vorticity is 0 because the vorticity is a Jacobian determinant, so that's true. Okay, so this is true, and then I'm kind of out of time, but we'll do this next time. But the point is, I can if phi is a 1 Lipschitz function, if I'm integrating phi over a small ball, within that ball I can replace phi by its value with the center, with errors who are comparable to the radius of the ball, which is epsilon v, which and the sum of those errors is like epsilon v alpha. And then I just have to evaluate this vorticity integral over ball, and that's a Stokes theorem calculation like the one I did in the sort of equivariant case. You end up integrating the let's see. So the integral of the vorticity over ball is the integral of this momentum density, J dot the unit tangent over the boundary of the ball. J is modulus squared times the phase gradient. But here we've made the simplifying assumption that the modulus is equal to 1. And so in this case, the integral of the vorticity over ball is really the integral of the phase gradient around the boundary of the ball, and that's the winding number. How many times the phase change, if I go around the ball, I'll see the phase change by integer multiple of 2 pi. And that's the winding number. Okay, and then there's some factor of a half someplace or pi. But that's the idea. And so and so to finish the proof of this lemma, we'll see why we can reduce the general case. I mean, what I'll do is I'll say, given a function whose who satisfies the hypotheses above, whose modulus is only bigger than half outside these balls. I'll modify it in a way that changes things very little, that doesn't change the vorticity, doesn't change the energy, and allows me to reduce that more general case to the case I've just discussed, which I'll do in a bit more detail next time also. Okay, so that's it for today, and sorry to run a bit over time. And if there are any questions, I'll be happy to answer them if I can. Okay, if there are no more questions, I'll just continue writing. Well, no, actually, I won't write this out. I'll finish this easy proof on Wednesday. But so what this does is it'll reduce the proving of these. So there's a, let's see, is there a question? Okay, so there's a question, good question. Can you explain why the set where psi is less than 1/2 corresponds to the set where the vorticity is not 0? So this is this is an assertion I made, and this is the explanation is that this is the meaning of the lemma. The lemma we're proving says, or the, did I state as a lemma? Okay, so next time I'll state a lemma, but the lemma is that these assumptions imply this conclusion. And so what this says is, if I can find this this set, if I can cover this set where the modulus is small with these nice small this unit of balls whose rate I add to a small number, then that's really telling me the vortex is strongly concentrated near those points. And yes, and so this assertion is a kind of a informal statement of the lemma that we have not written out, but that we're proving right now. And so we can see for sure that that if the modulus is 1, if I really have regions where the modulus is 1, then the vorticity is equal to 0 there. And then one can believe that if the modulus is close to 1, then the vorticity is small, or I mean, well, okay, that's not so obvious, but I'll finish this proof on Wednesday, and I hope it will clarify this. Okay, having a dismal day in Toronto. It's raining. Okay, I'll just walk around. Okay, still no questions. No more questions. Okay, well, I'm impressed that some of you at least will sort of continue sitting here and not asking questions as long as the thing is open. But maybe I'll turn this off. And I'll stop the screen sharing. Oh, actually, let me maybe I'll. This is not super well organized, but I guess I'll add this to the chat, the file. But the eventual there'll be better versions of this later on, probably. So chat. Okay, so these notes are available in the chat if you are interested. And so I'll leave them there for a few minutes and then I'll shut down the meeting. Maybe I'll stop recording. Okay, another question, is log epsilon considered a good growth rate, physically speaking? Well, here's the thing about log epsilon, or logs in general. So of course, a log of 1 over epsilon diverges as epsilon goes to 0, but it diverges very, very slowly. And so there's sometimes when it's appropriate to think of log of 1 over epsilon as being sort of basically infinite, diverging factor. In other cases where it's appropriate to think of as being basically 1, because it's if you're comparing it to any epsilon to the alpha, any power of epsilon, then it's basically 1. It's or a negative power. But so in this we right, in these problems, I always want to think of log epsilon as being some, a huge number, which, for it really to be huge, I need epsilon to be, I don't know what, 10 to the minus 50 or 10 to the minus, log epsilon is not actually very big until epsilon is, it's incredibly tiny. But the point is, it's sort of the right thing that appears here. It just appears naturally in all of these things for the reasons we've seen that one always ends up integrating factors of 1 over r dr from epsilon to 1, and that's just the way the energy concentrates in these problems, and so it's just an inevitable feature of life. In the same way, we saw a lot of log epsilons in the Euler equations. So there are these vorticity concentration lemmas, which also involved if you had vorticity concentrating on a for similar reasons, if you had vorticity concentrating on a ball of radius epsilon, then the energy would diverge like log of epsilon. So, okay.